Good morning, everybody, and welcome to the third entry in the HyperMu devlog, where I'm excited to share a new set of tests correlating real-world data to our simulated results. HyperMu is a written-from-scratch multi-body vehicle dynamics simulation written in Python. Intuitively, HyperMu is a virtual 7-post shaker rig, but has additional functionality where it can replay lateral and longitudinal acceleration, synthetic or captured from telemetry, through the vehicle model's center of mass. For this reason, I sometimes think of it as a 7 plus 2 post virtual shaker rig. HyperMu focuses on predicting values critical to vehicle performance, but that are impossible to directly measure in race conditions. Before talking about the new correlation tools, I want to return to the disclaimer at the beginning of the video. Any correlation presented today does not rise to the standard of validating HyperMu as safe for real-world use. So please just consider this video as strictly academic. That said, let's jump into it. I happen to have a set of automotive corner scales, which allow me to measure the weight at each tire while my race car is at rest, with or without me in the driver's seat. This at rest data is used to parameterize the HyperMu vehicle model. Then I can mimic a real shaker rig by raising each corner scale by a known distance and measuring the corresponding change in weight distribution. This mode of suspension deflection is similar to warp, where diagonally opposed wheels trap apart. I do this at each corner of the car, and the result is a data set of static floor offsets and corresponding weight transfers. To have any confidence in HyperMu's abilities, its predictions should be reasonably close to these data. Let's also consider that these data are static. So we're isolating the kinematics, compliance, and spring rates of the chassis and the tires. Effects from inertias, damper rates, and hysteresis are not relevant in this experiment. That said, for fully dynamic correlation results, you can look at the first devlog entry. It's far from perfect, but it is getting better, and I hope to talk more about that soon. To replicate this scenario in HyperMu, I built a new force function which elevates the correct wheels, the correct distance, and parameterized two new vehicle models from the most recent baseline data, one with and one without the driver, yours truly. We can then create our HyperMu vehicle model using the same commands as before. Only now you'll notice a brief initialization is run, which allows the vehicle model suspension and tires to settle and stores that as the initial state for all subsequent runs. This eliminates noise in the first second or two of our actual tests. Next, we specify the static correlation experiment we want to run and which set of data we want to use as our control. In this case, I just stored the data from the scale in YAML files. As the simulator begins, the visualization will guide us through the results and the errors. You'll notice the simulation being started 4 times. Each time represents one wheel being displaced, the chassis being given time to settle, and the final weight transfers recorded. And here's that visualization. Each figure in each corner of the plot represents the reaction of tire load for that corner of the car. For example, in the top right here, you can see that the tire loads on the tire loads of the front right tire initialize identically every time, but then react differently depending on which wheel in the chassis is being elevated in warp. The black lines represent the real world data that we measure the correlation against. The errors are written below, and we can see that HyperMu is anywhere between 10 to 15% off in its estimation of weight change on a single tire. It's a decent result, but I was hoping for better, and we need to understand where the errors might be coming from. Firstly, the real-world vehicle clearly has some asymmetries in its weight transfer, shown by the differences in the black lines. This can be down to uneven tire pressures, hidden suspension preloads, differences in shock pressures, or anything like that. HyperMu's results, meanwhile, are fairly symmetric in the steady state, at least, failing to account for these imperfect variations in the chassis from corner to corner. Another factor affecting accuracy, possibly the most important one, is HyperMu's tire model. Tire stiffness and damping, as you're probably aware, is highly nonlinear, affected by tire pressure, displacement, and even things like camber angle. Despite this, HyperMu has been using a linear tire stiffness and damping model until now, partially because it was a quick start to get the simulation running, but also because there haven't been significant correlation tests until now to expose it as a significant source of error. Finally, these results are really sensitive to the chassis' torsional stiffness, since that's the only parameter that enables the stiffness of one axle to affect weight transfer on the other. Our vehicle is an E46 BMW, which has a nominal chassis torsional stiffness of 12,500 Newton meters per degree. But it's impractical to measure how much of that stiffness has been lost due to age, miles on public roads, miles on race courses, and various modifications cutting into the unibody, such as fender clearancing. Our inability to measure this accurately also contributes to the error. So the vehicle model defaults to the factory original 12,500, but this is an educated guess. As a quick tangent, and to further exercise HyperMu, and to prove how important chassis flex is to chassis tuning, let's run an experiment where we set the chassis torsional spring rate to 0. Without any chassis stiffness and no g-forces, we would expect there to be no weight transfer on either axle in this warping scenario. So we'll remake the model and rerun the scenario. The results confirm our intuition, showing no weight transfer on any tire when the torsional stiffness is set to 0. You can see some signal as the tires respond to the shaker floor moving into position, but it settles to the original value. While I wish that the errors in the conventional loading case were smaller, it's always cool to see the model behave correctly, even in theoretical, goofy scenarios which the simulator wasn't even designed for. The point being, with a more accurate torsional stiffness value, I would expect the error to be significantly better. And finally, for thoroughness, let's go ahead and run the vehicle model and data combo for the vehicle model without a driver. We'll go ahead and create a new vehicle model for that and run the simulation again. Overall, the results are decent, again, trending between 10% to 15% error, and they show that HyperMu is heading in the correct direction for strong real-world correlation. I want the errors to be lower still, and I do believe that a more sophisticated tire model will help. However, it's unclear how to more accurately measure the torsional stiffness of the chassis and various chassis asymmetries. So thank you all for watching this far into the video. I've been working on HyperMu in a couple of different directions for the past 2 months, so there's a big backlog of cool things to share, and hopefully I can start putting out these videos a little bit more consistently. Consider sharing with a fellow gearhead if you found this interesting, and I'll see you next time. Have a great day, and thank you again.